metal-organic frameworks, design principles, synthesis strategies, and emerging applications in sustainable technologies. Metal-organic frameworks, MOFs, have emerged as a transformative class of porous crystalline materials with exceptional structural tunability, ultra-high surface areas, and diverse functionalities. Constructed from metal ions or clusters coordinated to organic ligands, MOFs exhibit unique physiochemical properties that enable applications across catalysis, energy storage, environmental remediation, and biomedicine. Despite rapid progress, challenges such as limited stability, selectivity, and scalability persist for pristine MOFs. Recent advances in MOF-based composites and synthetic methodologies have significantly expanded their functional scope and industrial relevance. This video provides a comprehensive overview of MOF structure, classification, synthesis strategies, governing factors, and applications, with emphasis on their role in sustainable technologies. The increasing demand for environmental sustainability, driven by rapid industrialization and associated pollutant emissions, has intensified the search for advanced functional materials capable of mitigating ecological impact. Among these, metal-organic frameworks, MOFs, have gained considerable attention as versatile platforms for catalytic transformation, pollutant capture, and energy-related applications. MOFs are crystalline, porous materials formed through coordination bonds between inorganic metal nodes, commonly referred to as secondary building units, SBUs, and organic linkers. This modular assembly leads to periodic network structures with exceptionally high internal surface areas, typically 500 to 7,000 square meters per gram, tunable pore architectures, and diverse chemical functionalities. Their structural versatility, combined with controllable porosity and functionalization, distinguishes MOFs from traditional porous materials such as zeolites and activated carbons. Since their conceptual development in the late 1990s, notably pioneered by Omar Yaghi, the field has expanded rapidly, with tens of thousands of MOF structures reported. Their adaptability has enabled applications in catalysis, gas storage and separation, sensing, drug delivery, and energy conversion. However, intrinsic limitations, including poor stability under certain conditions, low selectivity, and recyclability challenges, have motivated the development of MOF-based composites and hybrid materials. Structural features and design principles. MOFs are composed of inorganic nodes, metal ions or clusters, interconnected by multi-topic organic ligands such as carboxylates, phosphonates, sulfonates, and nitrogen-containing heterocycles. The geometry and connectivity of these components determine the topology, pore size, and functionality of the resulting framework. The concept of reticular synthesis enables the rational design of MOFs with predetermined structures by selecting appropriate building units. Structural diversity arises from variations in ligand connectivity, ditopic, tritopic, or higher, coordination geometry, and synthetic conditions. MOFs can exhibit a wide range of geometries, including cubic, octahedral, and trigonal architectures, often with hierarchical pore systems. A defining characteristic of MOFs is their permanent porosity, which allows guest molecules to be adsorbed, stored, or selectively transported. The pore environment can be chemically modified to introduce specific interactions, thereby tailoring adsorption selectivity and catalytic activity. Classification and nomenclature. MOFs can be classified based on their structural motifs, composition, and topology. Prominent families include asoreticular MOFs, IAR MOFs, zeolitic imidazolate frameworks, ZIFs, porous coordination networks, PCNs, Materials Institute Lavoisier, MIL, frameworks, University of Oslo, UIO, structures, and porous coordination polymers, PCPs. Asoreticular MOFs are derived from a common structural scaffold with systematically varied linker lengths, enabling pore size tuning. ZIFs, characterized by imidazolate linkers, exhibit zeolite-like topologies and exceptional chemical stability. MIL frameworks, typically based on trivalent metals and carboxylate ligands, are notable for their large pore volumes and structural flexibility. UIO-type MOFs, constructed from zirconium clusters, are distinguished by their remarkable thermal and chemical stability. Nomenclature in MOF chemistry often reflects either structural similarity or the institution where the material was first synthesized, such as HKUST, DUT, or NOT families. The term MOF broadly encompasses hybrid organic-inorganic coordination networks with permanent porosity. Synthesis strategies. The synthesis of MOFs involves the coordination-driven self-assembly of metal ions and organic linkers under controlled conditions. Various synthetic routes have been developed to tailor crystal size, morphology, and porosity. The solvothermal method remains the most widely used approach, involving reactions in sealed vessels at elevated temperatures and pressures. Hydrothermal synthesis, a variant using water as solvent, is particularly relevant for environmentally benign processing. Microwave-assisted synthesis enables rapid crystallization and uniform particle formation through efficient dielectric heating. Electrochemical synthesis offers a green alternative by generating metal ions in situ via anodic dissolution, eliminating the need for metal salts. Mechanochemical synthesis, conducted via grinding or ball milling, provides a solvent-free and energy-efficient route, although it may limit crystal size and porosity. Sonochemical methods utilize ultrasonic irradiation to induce rapid nucleation through cavitation effects, producing nanoscale MOFs. Additional techniques such as ionothermal synthesis, spray drying, diffusion methods, and chemical vapor deposition further expand the synthetic toolbox. Each method presents distinct advantages and limitations in terms of scalability, crystallinity, energy consumption, and environmental impact. Factors influencing MOF formation. The synthesis and structural characteristics of MOFs are highly sensitive to several parameters, including the choice of metal ions, ligand type, solvent system, pH, temperature, and reactant ratios. Carboxylate-based ligands are particularly versatile due to their multiple coordination modes, while nitrogen-containing heterocycles offer distinct coordination geometries. Mixed ligand strategies enable the construction of complex architectures with enhanced functionality. Reaction conditions influence nucleation and crystal growth kinetics, thereby affecting pore size distribution, phase purity, and structural stability. Careful control of these parameters is essential for designing MOFs with desired properties. MOF-based composites. To overcome the limitations of pristine MOFs, hybrid materials have been developed by integrating MOFs with polymers, metal oxides, carbon materials, nanoparticles, and polyoxometalates. These composites exhibit synergistic properties, including enhanced stability, improved conductivity, and increased catalytic activity. MOF-derived porous carbons, obtained through pyrolysis, have shown promise in energy storage applications. Similarly, incorporation of graphene oxide or metal nanoparticles can improve electrical conductivity and catalytic performance. Such hybridization strategies are critical for translating MOFs into practical applications. Applications. Gas storage and separation. The high surface area and tunable porosity of MOFs make them ideal candidates for gas storage, including hydrogen, methane, and carbon dioxide. Adsorption capacity is influenced by pressure, temperature, and pore characteristics. MOFs have demonstrated superior performance compared to conventional porous materials, particularly in hydrogen storage and carbon capture. Catalysis and energy conversion. MOFs and their composites serve as efficient catalysts in heterogeneous catalysis, photocatalysis, and electrocatalysis, including oxygen reduction, hydrogen evolution, and carbon dioxide reduction reactions. Their high density of active sites and structural tunability enable precise control over catalytic processes. Biomedical applications. MOFs have gained attention as drug delivery platforms due to their high loading capacity, tunable pore size, and controllable release behavior. Strategies such as in situ and post-synthetic encapsulation enable the incorporation of therapeutic agents. pH-responsive MOFs allow targeted drug release in tumor environments, while magnetic MOF composites facilitate controlled delivery in imaging applications. Electrochemical energy storage. MOFs and MOF-derived materials are increasingly explored in lithium-ion batteries, supercapacitors, and other energy storage devices. Their porous architecture and compositional diversity enable high capacity, improved cycling stability, and enhanced rate performance. Environmental remediation and membrane technology. MOF-based membranes exhibit exceptional selectivity and permeability for water purification, desalination, and pollutant removal. Applications include microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Their tunable pore structures enable efficient separation of ions, organic molecules, and heavy metals, making them promising materials for sustainable water treatment technologies. Challenges and future perspectives. Despite significant progress, several challenges hinder the large-scale deployment of MOFs. These include limited chemical and mechanical stability under operational conditions, difficulties in scalable synthesis, and high production costs. Additionally, issues related to recyclability and long-term performance must be addressed. Future research should focus on the rational design of robust MOFs, the development of green and scalable synthesis methods, and integration into functional devices. Advances in computational modeling, machine learning, and high-throughput synthesis are expected to accelerate the discovery of next-generation MOFs with tailored properties. In conclusion, metal-organic frameworks represent a versatile and rapidly evolving class of materials with significant potential across multiple technological domains. Their unique combination of high porosity, structural tunability, and functional diversity enables applications ranging from energy storage and catalysis to environmental remediation and biomedicine. Continued innovation in synthesis, composite design, and application-specific optimization will be crucial for realizing the full potential of MOFs in addressing global sustainability challenges.